Alright, so here they're asking what would be the coefficient of H plus ion in the balanced net ionic equation for the following reaction in acidic solution. Okay, and the reaction is S2O32 minus plus Cr2O72 minus gives you S4O62 minus plus Cr3 plus. This is the reaction given to you. You need to balance it in acidic medium. So let's go ahead and start with it. So you have S2O32 minus plus Cr2O72 minus giving you Cr3 plus S4O62 minus, and we need to balance this in the acidic medium, very important. All right, good. So now what we'll do is we will balance the equation. So let's see. First, you have to find out that which element is undergoing oxidation, which element is undergoing reduction. So first, let's do that. Pretty easy for chromium here. It's going to be in +3. On the product side, on the reactant side, you have dichromate ion, where I'm sure by now you know that chromium is in its highest oxidation state, that is +6. But still, because we're still beginning with it, it's okay to take your time and figure it out. Okay, 7 into -2 is equal to -2. So C minus 7 is equal to -1. C is equal to +6. And +6 is the oxidation state of chromium here. Done? Okay. Now we come to S2O32 minus thiosulfate ion. So here I'll say the oxidation state of sulfur is S. So 2S plus 3 into -2 is equal to -2. So you get S minus 3 is equal to -1. You get S is equal to +2. So here sulfur is in +2 oxidation state in the thiosulfate ion. Now last you have S4O62 minus, and here let's say the oxidation state of sulfur is S. So 4S, or let's call it 4S1 because why confuse ourselves, plus 6 into -2 is equal to -2. So what do you get? You get 2S1. 2S1 minus 6 is equal to -1. So you get 2S1 is equal to +5. S1 is equal to +5 by 2. That is nothing but +2.5. So here you will have +2.5 as the oxidation state of sulfur. Remember, this +2.5 is nothing but the average oxidation state of sulfur, alright? Average oxidation state. Very important, because when you draw the structure, it is possible that one sulfur will have some other oxidation state, the other will have some other oxidation state. Absolutely okay. What we care about, average oxidation state, is +2.5. So now, let's see. Sulfur went from +2 to +2.5. +2 to +2.5 is nothing but oxidation. What is going to be the N factor? N factor is going to be, first of all, check the change in oxidation state. It is 2.5 minus 2. Change in oxidation state is 0.5. How many such sulfur atoms do you have on the reactant side? You have 2 such sulfur atoms. So 0.5 into 2, you will get 1. Okay, N factor for this change is 1. Now when you come to the dichromate ion, here you have chromium in +6 oxidation state becoming chromium in +3 oxidation state. This is definitely reduction. Yeah. And what is the change in oxidation state? So +3 minus +6, this is going to be -3. Now we only care about the magnitude, not the sign. So 3 multiplied by number of chromium atoms on the reactant side. 3 into 2, 6. Your N factor here is equal to 6. Now what will we do? We will cross multiply it. So here you will write, here you will write 1, which is as good as not writing anything. And with S2O32 minus, you will write 6. Okay, so this is what we get. Now I'll clear this out. And now what you can see is that we have reached the second step where we balance the elements that are undergoing oxidation and reduction. Okay, so see, on the reactant side, you have 6 into 2, 12 sulfur atoms. On the product side, you have only 4. So 12 by 4, 3 is the stoichiometric coefficient of S4O62 minus. So I'm going to write 3 here, which means you will get 12 sulfur atoms on each side. Now, on the reactant side, you have Cr2O72 minus, okay, which means you have 2 chromium atoms in the dichromate ion, right? On the product side also, we need to add a 2 because of this. Okay, so the elements that are undergoing oxidation and reduction have been balanced. Now we need to balance oxygen atoms. So you can see here on the reactant side, what do you have? You have 18 plus 7. You have 25 oxygen atoms, whereas on the product side, you have only 18. Which means what? Which means I'm going to add 7H2O here. Alright, I add 7H2O on the side that has lesser number of oxygen atoms so that I can balance the oxygen atoms. So I got a total of 25 oxygen atoms on each side. Now I am simply left with balancing the hydrogen atoms, and because this is acidic medium, I will need to use H plus ions or protons to balance the hydrogen atoms. So here you have 0 hydrogen atoms on the reactant side and you have 14 hydrogen atoms on the product side. So go ahead and write 14H plus on the reactant side. So your final balanced equation is this. You have 6S2O3 2 minus plus Cr2O7 2 minus plus 14H plus is giving you 2Cr3 plus 3S4O6 2 minus plus 7H2O. Okay, this is what you get. So now you go back to the options. We were looking for the coefficient of H plus in the balanced equation, right? So what did we get? 14H plus, which means 14 is the right answer. So option C, 14 is going to be the right answer to this question. Okay, so here they're asking which of the following is true regarding decomposition redox reaction. We'll read the statement, we'll write down what sort of a reaction it is. If it is decomposition, then that is going to be our right answer. And let's get started. So you have option A. Same element of a single compound undergoes oxidation and reduction. What is this? This is nothing but your disproportionation reaction, correct? This is your disproportionation reaction. Okay. Now, you have option B. Different elements of a single compound undergo oxidation and reduction. This is your standard redox reaction, right? This is what happens in most of the redox reactions. So this is not disproportionation. This is just your normal redox reaction. So yes, so far it is fitting in with the idea of a decomposition reaction. Let's see what's happening. Now, you have option C, same element of different compounds undergoes oxidation and reduction. Okay, so if the same element from different compounds is undergoing oxidation and reduction to give you one single product, then what is it? It is comproportionation reaction, which as I keep telling you, is nothing but disproportionation reaction, but seen from the reverse end. So this is comproportionation. Option B is very much decomposition reaction, where you have one single compound uh, in which you have two different elements which undergo oxidation and reduction, and yes, that is decomposition redox reaction. So option B is going to be the right answer to this question. All right, so here they're saying which one of the following statements is incorrect in relation to ionization enthalpy. What is ionization enthalpy? Basically, the amount of energy we need to supply to the setup where you are removing an electron from a neutral gaseous isolated atom. Okay, that is going to be the ionization enthalpy, the ionization energy, whatever you want to call it. So let's see, we'll read the statement, we'll mark true or false against it. Whatever is false is going to be the right answer to this question. So you have ionization enthalpy increases for each successive valence shell electron. So what are they saying? They're saying that basically IE2 is greater than IE1, this is greater than IE3, and so on. Yes, this is definitely true, right? Why? Because as you start removing, let's say you remove the first electron, right? Whatever electrons are left, those electrons are pulled by the nucleus more strongly. So the effective nuclear charge is increasing on those electrons. So it becomes increasingly difficult for us to keep removing the electrons from the valence shell after that. Okay? This statement is true. Option B. The greatest increase in ionization enthalpy is experienced on removal of electron from core of noble gas configuration. Think about it. Let's say you have magnesium. Okay. So in case of magnesium, you have what? You have your inner shell, that is your neon. This is your core electrons. Okay, and then you have 3s2. Correct? Now, you remove one electron, make magnesium plus, you will have neon 3s1. Then you will have magnesium 2 plus, you will basically have neon 3s0. Now, if I want to remove one electron, if I want to make magnesium 3 plus, here I will have to disturb the core electrons, and for that it will require a lot of energy. Okay, a lot of energy will be required, because we are disturbing the core electrons, we are disturbing the core noble gas configuration. Noble gas configuration is really stable, ns2 np6 configuration, but we are going ahead, we are trying to remove one electron from that p orbital, right, which will make it a highly energetically taxing process. Okay, so yes, this statement is true that you will observe the greatest increase in ionization enthalpy when you disturb the core electrons. True. Option C, end of valence electrons is marked by a big jump in the ionization enthalpy. True, right? Mostly whatever we said previously. Now, if you look at it in this case, in magnesium, 3s is your valence shell. The moment you've exhausted the valence shell and still you're trying to remove the electron, you try to make magnesium 3 plus. That is when you start disturbing the core electrons. So same thing, yes, the moment you exhaust your valence shell and come to another shell, you will observe a great difference in energy. This is true. Okay, cool. Then you have option D. Removal of electrons from orbitals bearing lower n value is easier than from orbital having higher n value. Okay. So think about it. Wherever you have a higher value of n, there your electron is more loosely bound to the nucleus, which means it's more easy for us, it's more feasible to pull out the electron. But if you have a lower value of n, then it is closer to the nucleus, right? If it is closer to the nucleus, it's more tightly bound to the nucleus. Yes, if it is more tightly bound to the nucleus, then you need more energy to remove that certain electron, right? Which is why it becomes more difficult to remove an electron which is closer to the nucleus. So it is more difficult to remove an electron with a lower value of principal quantum number, or n, than it is to remove an electron with a higher value of n. Okay, understood? Which means the statement here is false. And if it is false, then it becomes the right answer to this question. So option D is going to be the right answer to this question. So in this question, they're saying that a 300 grams 30% weight by weight NaOH solution is mixed with 500 grams 40% weight by weight NaOH solution. What is the molality of the final solution? Okay, so first of all, what is molality? Molality is basically number of moles of solute. So number of moles of solute, here you have NaOH, so I'll write NaOH, per kg of solvent, not solution. Okay, so per kg of solvent, which in this case is going to be water. All right, let's get started. So you have solution A, which is 300 grams of 30% weight by weight NaOH. Okay, so how much NaOH is in here and how much water is in here, we need to find that out. So NaOH, let's find out first. So mass of NaOH, or if this confuses you, just write weight of NaOH. You have 30 by 100 into 300, okay, which is nothing but 90 grams. Okay, now weight of water is going to be 300 minus 90, which is nothing but 210 grams. Sorted? Great. Now we have solution B, which is 500 grams of 40% weight by weight NaOH. Correct? So, what is the weight of NaOH in solution B? You have 40 by 100 into 500. Okay? So, this is going to be 40 into 5, 200 grams. Okay, cool. Now, what is the weight of water? You have 500 minus 200. So, this is going to be 300 grams. Done? Okay. Now, look here. Total weight, like when I come to the final mixture in which we have mixed solutions A and B both. So here weight of NaOH is going to be what? Weight of NaOH from A plus weight of NaOH from B, which is 90 plus 200. Okay, so here you will have 290 grams. Now weight of water is going to be Weight of water in A plus weight of water in B. So 210 plus 300. This is going to be 510 grams. Now let's get down to calculating molality. You have to find out number of moles of NaOH. So if you want, you can find it out here itself. Number of moles of NaOH is going to be 290 by 40. Okay. Keep it as 29 by 4. If you want to simplify, you can simplify it. Whatever you want to do, it's up to you. If you want to simplify, sure, we can write it as 7.75. Oh, sorry, 7.25. Okay, 7.25 moles of NaOH. Done. So now you have 7.25 moles in 510 grams of solution. Convert this to kilograms. So you can write 510 by 1000 or simply 0.510 kg. Correct? Same thing, right? Okay. Now, instead of 0.510, I want to approximate it to 0.5, and then that 0.5 I'll write it as 1 by 2. So I will get 7.25 multiplied by 2, multiplied by 2 molar, which is nothing but 14.5 molar. Remember, your value will come very close to 14.5, but slightly lesser because we made one approximation. We took 0.51 as 0.5. So keep your eyes and ears open for that approximation. Here we got 14.5. The value that I'm actually expecting to see in the options has to be slightly lesser. Very slightly, okay? So I got 14.5 molar. Your options are 1.422 molar, which is much lesser, so you can ignore it. 14.22, yes, this is what I was telling you, right? Slightly lesser, this is correct. 15.22 is greater, slightly greater, not required. Option D, none of these, we don't care. Okay, the right answer here is going to be 14.22 molar. So here they're saying that you're given with a reaction Na2HASO3 plus YBrO3 plus HCl is giving you NaBr plus H3ASO4 and NaCl. Okay, and you have some stoichiometric coefficients X, Y, and Z mentioned. The value of X, Y, and Z in the above redox reaction respectively are going to be what? Okay, so we have to balance the reaction first. Okay, that's the fundamental understanding we have here. So let's go ahead and do that. So you have Na2HASO3, right? Plus NaBrO3, sodium bromate, plus what do you have? HCl. Okay, this is giving you NaBr. Okay, I'll write NaBr here, plus NaCl here. And what else do we get? H3ASO4. H3ASO4 here. Okay, done? Great. Now what we'll do is we will find out the oxidation state of the respective elements. We will find out which species is which element is undergoing oxidation, which element is undergoing reduction, and then we will go ahead with our normal oxidation number method, cross multiply, find n factor, then cross multiply, all that we'll do. Okay, let's get started. So first, chloride is the easiest, right? Okay. Then you have bromide, so -1 here. Then you have H3ASO4. We have no option but to calculate. So let's go ahead and calculate. So let's say arsenic is in the oxidation state of AS. Okay. +3 due to hydrogen, plus 4 into -2 due to oxygen is equal to 0. So AS +3 minus 8 is equal to 0. AS is equal to +5. So here arsenic is in the oxidation state of +5. Okay. Now we need to look at NaBrO3, sodium bromate. Okay, the moment you see bromate, I hope you remember that bromate has bromine in +5 oxidation state. If you don't, let's calculate. So sodium will contribute +1, plus let's say bromine is in Br oxidation state, +3 into -2 is equal to 0. Okay, so here you have Br +1 minus 6 is equal to 0. So Br is going to be equal to +5. So here bromine is in +5 oxidation state, like I had mentioned earlier as well. Now you have Na2HASO3. That's the compound you have. So here sodium is in +1, hydrogen is in +1, oxygen is in -2. You have to find out for arsenic. So I'll say the oxidation state of arsenic here is A, +2 due to sodium, +1 due to hydrogen, +3 into -2 due to oxygen is equal to 0. So you have A +3 minus 6 is equal to 0. You have A minus 3 is equal to 0. A is equal to +3, which means arsenic here is in +3 oxidation state. And yes, we are done with everything. Now let's find out what is undergoing oxidation and what is undergoing reduction. Okay, So here you have arsenic going from +3 to +5. +3 to +5 is what? +3 to +5 is definitely oxidation. Okay. N factor, 5 minus 3, 2. How many such arsenic atoms? 1. So 2 into 1, you will have 2 as the N factor. Then you have NaBrO3. Okay. In case of NaBrO3, which is going to NaBr, you can see that bromine went from +5 to -1. +5 to -1 is your reduction half. Okay. And what is going to be the N factor? -1 minus +5. So -1 minus 5 is -6. We need the magnitude, so we have 6 here. Okay. And N factor is going to be only 6 into 1 because you have only one such bromine atom on the reactant side. Done. You can see that chlorine in HCl and NaCl, both places exists as chloride, so we don't have to worry about it. It has not undergone oxidation or reduction. It's just there. It's sitting. Okay. Now cancel this out and cross multiply. So you have cross multiplied and this is what you get. Right. Now, you can see that first thing you need to do is you need to balance the element that is undergoing oxidation and reduction. So put 3 here to balance the arsenic, and bromine is already balanced. Now, we have to balance the other elements which are not undergoing oxidation and reduction. Keep oxygen and hydrogen aside for a while. You have other auxiliary elements or atoms, like you have sodium and you have chlorine. You have to balance these things. Okay. So you can see on the reactant side, you have 3 2 6 plus 1, 7 sodium atoms. On the product side, you have 2 sodium atoms. Okay. So what we will do is we will add a 6 here. Okay. I don't want to disturb NABr because that will change the number of bromine atoms, which is actually undergoing oxidation, no, reduction. Okay, it's undergoing reduction, so I don't want to disturb NABr. Okay, so this is done. Now we have to balance the chlorine atoms on the reactant side respectively, because here now we said that we have 6 chlorine atoms on the product side. So we'll place a 6 here as well, no problem. Okay, now we have to balance the oxygens and the hydrogens. So oxygens, let's see. On the reactant side, you have 3 3s are 9 plus 3. 12 oxygen atoms. On the product side, you have 3 4s are 12. Oxygens balanced. Great. Okay, what about hydrogen? On the reactant side, you have 3 plus 6. You have 9 hydrogen atoms. And on the product side, you have 3 3s are 9. So hydrogen is also balanced. So see, we didn't really have to go into the medium of it. We didn't have to use extra water molecules to balance this. This reaction has been balanced just by looking at the spectator ions. Okay. So now what were they asking for? X, Y, and Z. X is with Na2HASO3, so this is 3. Y is with NaBrO3, so this is 1. Z is with HCl, so this is 6. So 3, 1, 6 as an option B. So option B is going to be the right answer to this question.